Okay. So my Zoom background is the one of a conference I was also chairing yesterday. So that's the new time of online conferences, is to be involved in many of these talks at the same time. So welcome everybody back to the Frontiers workshop. And today we have a change in the program that you have probably seen, but we're very happy to have on board Tobias Stauber, who has been working on twisted graphene actually for a very long time. So I think probably Tobias is the speaker, or one of the speakers that's been working on twisted graphene since many years already, long time before the results of Pablo came out. So I'm not sure he's going to talk also about those earlier works, but today he's going to speak about chirality in twisted bilayer graphene as an interesting topic, novelty recently found. And Tobias from the Instituto de Ciencia de Materiales in Madrid. So I leave the floor or the screen to you now, Tobias, and thanks again for accepting to speak at our workshop.
All right, so thank you very much, Frank, for this possibility to present our work here. My name is Tobias Stauber. I work in Madrid Material Science Institute, and my work is, as you said, on superconductivity and chirality in twisted bilayer graphene. And after 2 weeks of this workshop, it's probably not necessary to introduce the topic, but I just want to pay tribute to the early experimental works that really boosted the whole field in a tremendous way. And this was definitely the work by Pablo Jarillo Herrero's group in MIT, where they saw not only in the two terminal conductance this one particle transport gap, but also this gap inside the valence and the conductance bands, which cannot be explained by the typical one particle band theory. So you need something more, and this was the first indication that one can tune the effect of interaction by changing the twist angle of this twisted bilayer graphene system. Now, the surprise was even nicer when they lowered the temperature, and then they saw that this conductance actually shooted up again close to this half-filled case. And this was the first indication that there was superconductivity also present in this sample. And there were important works then also from Corey Dean's group in Colombia, and also Andrea Young. And let me also highlight now the work by Dmitry Afitov's group, where they saw that actually not only around half filling there are the domes present, but they spread out over the whole band of the valence and conduction bands. I don't want to go, I mean, there has been a lot of development after that, of course, and this has been presented also at this workshop. Let me only highlight that this typical critical temperature scale is between 1 and 2 and 10 K, and that there's a strong similarity to the phase diagram of the high TC group rates, where you also have an correlated state and mod state at half filling, and then upon electron or hole doping, these superconducting domes emerge. And between this pseudo gap and the Fermi liquid regime, there is a strange metal regime, which is actually also seen in twisted bilayer graphene, and which is going to be a topic of this talk. So let me come to the outline of my talk. I will talk first on our theory on superconductivity and linear T resistivity. This work was done in close collaboration with Jose Gonzalez. He's also working at the CSIC in Madrid. And the second part is devoted to the chiral response, and then also the effects on coherent transport. And this work was in close collaboration with Guillermo Gomez Santos. He's a professor at the Autónoma of Madrid. All right, so let me start with the Cohn-Luttinger superconductivity topic, and let me remind you that these were very interesting times just after this Nature publication by Pablo's group. There were many theory groups, of course, jumping on this topic. And after 2 or 3 months, there were a bunch of papers presenting different theories. And we were one of those. So let me kind of put you on the map what our theory is about. So we were working on an electronic mediated pairing mechanism. In contrary to phonon-electron interaction, and to a weak coupling approach. This means that we assume that the bandwidth is larger than the Hubbard U. This is not the flat band regime, actually. So we have to work at twist angles which are slightly above the magic angle, but I will show you that this is actually justified. And we believe that this superconducting instability might be triggered not from the clearly flat band regime, but slightly above. And the strongest point or difference is probably that we are really using microscopic models. So it's not an effective model, but microscopic models. This means that we are using the continuum model by João Lopes Santos, Nuno Pérez, and Antonio Castroneto, and later on Bistritzer and Al McDonald. And also we are working with the tight binding model. And we introduce lattice relaxation in several ways and change parameters. So what I'm telling you now is some kind of universal features that are actually present in all of these models. The mechanism is, we are considering is this Cohn-Luttinger mechanism, and this is an old proposal by Cohn and Luttinger more than 50 years ago. And it is related to this discontinuity of the Fermi surface. And due to screening of the quasiparticles, there will always open up an attractive interacting channel. And in order to have this mechanism present and relevant, there has to be a lot of screening. And screening can be provided by Van Hove singularities. So let me outline this. The dispersion of a typical toy model of a Van Hove singularity is given here with these inverse masses alpha and beta. And if these are small, alpha and beta, so if they are really, if these Van Hove singularities are very flat, you see that the resulting susceptibility can be very large. So it's not the logarithmic divergency that is important, but it's the prefactor. And we are looking for these small masses, and it will turn out that alpha and beta will actually be quite different also. So why Van Hove singularities? And I told you before, and as you know, superconductivity was found at half-filled filling factors or integer filling factors. One motivation can be this early work by Pablo Carrillo Herrero's group and the group of Jürgen Schmidt in the Max Planck Institute of Stuttgart. They saw independently that the Hall conductivity is changing sign at half filling. So here, this is this change of this Hall conductivity, and this one is related with a change of an effective mass. And this can be linked to a Van Hove singularity. So there seems to be experimentally they see that there seems to be a pinning of the Van Hove singularity at half filling. And this has been now with theoretical works also confirmed. So this is our starting point that Van Hove singularities might become the major key to understand this superconductivity. So let's see now what the valence band of the highest valence band looks like, the band structure at the Van Hove singularity. The Fermi line is this black line here, as you can see. And the Van Hove singularities are always there where the lines cross. So it's here. And then, of course, this is the zone boundary. So they cross also here and here. And so there are 3 Van Hove singularities. And they are at the endpoint. So this is what you would expect, that the Van Hove singularities in these Dirac systems are actually at the endpoint. Now, if you decrease the twist angle to a twist angle of 1.3 in this case, you see that the Van Hove singularity has moved away from the endpoint, but there are still 3 of them present. And now, at some certain critical angle, a Lifshitz transition occurs, and you have a doubling of the Van Hove singularity. So this Van Hove singularity moved inside, and now you have 6. So 1, 2, 3, 4, 5, 6. And for us, this is the onset of this superconducting regime, because the more Van Hove singularities you have, the more screening you can have, and then allow this Cohen-Lattinger mechanism to be active and to be relevant. Let me also notice that the flat band regime has a different structure. There you have an emergent C6 symmetry. You still have these 6 Van Hove singularities, so there's no problem in having the same mechanism that Van Hove singularities might be active, but we cannot treat this from our RG perturbative approach. We can rely on angles which are larger and then really justify this perturbative treatment. If you do the calculations now complete, you have to also include the other valley here. So both valleys included, and this means that you have 2 bands, an upper band and a lower band. And in both cases, there is this emergence of new Van Hove singularity. So also in the lower band and here also, there's this new emergence of this doubling. And this is our hypothesis now, that this Lifshitz transition actually leads to these ultra flat and also extended Van Hove singularities. If you, so let me come to the detailed calculations we do. We take one band structure of this would be the second highest valence band at an angle which is still above the flat band regime, and we locate ourselves at the energy of the Van Hove singularity. You see here that this Van Hove singularity is very extended, and so it's not like a cross. It's not isotropic, but it's kind of stretched out. And then we dope our system slightly below this, this energy. And this is now our Fermi surface. And you see that there are 2 patches. And we can now place the 2 Cooper pairs on top of it. And you see that they are the time reverse partners. They live on different valleys. I mean, the red and the blue lines indicate different valleys. And these Cooper pairs can now interact, and they can interact in the following way. They can interact and scatter, staying on the same patch here. But what they can also do is they can have an interpatch scattering. And therefore, the Cooper pair vertex is actually a matrix. And diagonalizing and analyzing the eigenvalues, one sees that you obtain a negative eigenvalue in the case if the interpatch Cooper pair vertex is larger than the interpatch. And this...
Sorry to interrupt. Some questions come in during the talk. They're in the Q&A box. If you can't see it, you can answer them directly, or I can read it to you.
At the moment, I cannot see them, sorry. Okay, I have to open them.
So I will read it to you. The question from Dimitri Chichinatse. And the question is, you mentioned extended Van Hove singularities. Did you mean higher order Van Hove singularities or just the doubling? please elaborate on that.
Yes, thanks for this question. I don't mean, by extended, I mean the following, that alpha and beta in this crude model of the von Hove singularity is different. If I go back quickly, this was the definition, the crude definition of a von Hove singularity. And if alpha and beta are now different and strongly different, this I would call extended von Hove singularity. And you can see it graphically here, that this cross is like stretched out in one direction rather than in the perpendicular one. So let me continue.
There's one more question.
Yes.
Can you see it now, or shall I read it? Oh, wait, this is in the chat. Okay, that's it says, but a large density of states means a low group velocity. If the electrons move very slowly, perhaps they cannot provide efficient screening if there's some intrinsic dynamics in the problem.
Yes, but as you can see, if this is flat, this is this formula which comes, this is from the toy model. At least from the toy model, you would expect that there's a strong screening due to this prefactor. All right. So this is actually an analytical result from coming directly from this dispersion relation.
To me, it sounds all right. I don't know if Fernando Solz is all right, but please continue.
All right. So what I wanted to say and continue is that we have a possible mechanism for an instability if this interpatch vertex is larger than the intrapatch vertex. So this is what we want to see and calculate. And we do this with a self-consistent RPA equation that relates the stressed Cooper per vertex. So this is the bare one. You have a momentum P and momentum minus P, and this scatters to a momentum K and minus K. And you can now parameterize these Cooper pairs by one angle that is related to the center of each patch. So this Cooper pair is labeled by this angle theta, and this Cooper pair is labeled by the angle theta prime. So this is the self-consistency equation, and we can now reabsorb the local density of states and will analyze this effective vertex here. So this is the calculation we have to do with our band theory that comes from the continuum model or from the tight binding model. And this is what we get. So this is the Cooper per vertex at one position. So one angle is set to 0, and then this is the other angle of the other Cooper pair. And as you can see, always the interpatch vertex is larger than the intrapatch vertex. And you can also see this from a different point of view, not only calculating the Cooper per vertex directly, but also from the susceptibility, which has a peak at Q equals 0. And just from an RPA expansion, this is the bare Cooper per vertex, and this is a dressed one. You see that this becomes dominant if K is minus K prime. And this shows that also in this picture, this interpatch contribution is of a lower order and therefore more dominant. So this all hints to this possibility of a superconducting instability induced by this Cohn-Luttinger mechanism and by electron-electron interaction. And we can now do this in a more systematic way. We can use the expansion in irreducible representation of the underlying lattice symmetry, C3V. And by Fourier transforming, we can see now and read off the representation just by collecting the higher harmonics. If the coefficients all belong to these higher harmonics, we know that it's the irreducible representation of A1. If they belong to these higher harmonics, they belong to the irreducible representation of A2. And if this is a degenerate eigenvalue, and we have this this change of coefficients, then we know that it's the two-dimensional representation. And with this at hand, we have this RG analysis, and with this standard procedure, we obtain a critical scale where this instability should occur that that amounts to approximately 1 Kelvin. And this is very, very close to what is actually seen. So we are confident that this might be reasonable to explain the experiment. Let me also mention that there are several possible instabilities belonging to different irreducible representations. And with a certain different perturbation, maybe there will be some shuffling, and we will have, for example, a two-dimensional representation that would maybe favor even chiral superconductivity. So this cannot be ruled out. So far, the highest negative eigenvalue is A1, and the parity is odd. So let me summarize the results. We obtain a order parameter that is almost isotropic around each patch. But since the parity is odd, you change sign going from one patch to the other. And this also means, since in real space it's odd, we obtain a triplet, spin triplet order parameter. And this is the phase diagram. We start from the Van Hove singularity, dope our system from below, and then for Hubbard U, we obtain first a superconducting instability that then crosses over to the spin density wave, which would then mark this correlated gap or this insulating phase. All this is, to my knowledge, still theory and cannot be directly assessed by experiments. But what can be assessed by experiment and what has been done?
Sorry to interrupt. There is a question.
Yes.
It's a little bit of a slide, a few slides back. Could you please explain more why the red and blue lines come from different values?
Okay.
Well, it's also there, yeah.
Sorry. Yeah, this one is, this one you mean, I guess?
Yes.
Well, okay, maybe I can show you this better on the other slide even here. This is the band structure now for only one valley. And the other valley can be obtained by flipping it around. So by parity. And we now collect, and this is actually the band structure that also comes out of the tight binding model. We have to now group them together. And the upper band is always the maximum of the two valleys, and the lower band is the minimum. You can compare this in the tight binding model. This comes out immediately, but if you start from the continuum model, you have to kind of collect them and regroup them in this way. And then you can see that this one comes from one valley, but this one comes from the other valley, because this is really then the time reversed partner, if you wish. And if you see the I mean, you always have then this the Cooper pair. If they change in parity, they also have to change the valley in order to be the Cooper pairs that are related with their time symmetric partner. So everything comes out when you do this grouping of a regrouping of these band structures. I hope this answered the question.
So it's good if you get the Q&A screen, Tobias. I think you can pull it up on, if you click on the bottom or on the top. There is a button somewhere.
Yes, it always disappears. That's why it does not stay clicked, and therefore I don't see the differences in my, the change in numbers.
Okay, then I will keep interrupting you if you don't mind, and people are encouraged to type their questions in the Q&A box.
Sure, and if there are some follow-up questions or if it was not clear, please insist, and I try to make it better with the next answer. Okay, so let me now come to a different topic, and this one is the linear T-resistivity. And this one, the linear T-resistivity has been seen by two different groups, leading groups, the one by Pablo Carrillo Herrero and the other one by Andrea Young and Corey Dean. And they both agree on that there is a linear T-resistivity, but they don't agree on the mechanism. This group favors electron-phonon mediated coupling, and if I'm correct, Pablo also favors more electron-electron mediated pairing mechanism. And one of the reasons is that this linear behavior can be seen down to very low temperatures, up to 0.5 Kelvin. And this is hard to understand if one invokes an electron-phonon interaction where you always have some cutoff, like the Grün-Eisen-Bloch cutoff or the Debye cutoff, where there should be some, where there should be this cutoff at higher temperatures. So
there was a question from Oscar Vavek.
Yes.
It's about the previous part. In this approach, TC will grow with increasing Coulomb repulsion. Correct? Question mark.
Is this approach T will increase? Okay. Let me. Thank you. I guess Oscar was referring to this first diagram here.
Yes, I think so. And
you see that this is the instability or this eigenvalue, and it grows. This eigenvalue grows, and therefore TC grows with Hubbard U. So this is probably what was your question, and I was not having time to get into this in more detail. But this is the negative eigenvalue minus 0.5 at some certain Hubbard U, and of course it would be smaller than for a smaller Hubbard U.
Okay.
All right. So let me highlight that there is a kink at this linear behavior. So this kink comes here at about 6 Kelvin, and I will comment on this, and we try to explain this. Again, our theory is based on the same as before. So we are locating ourselves at the Van Hove singularity, and then dope our system slightly away from it. And then you see that there are these very elongated, and this I call this extended Van Hove singularity. So this is due to this extended Van Hove singularity that you have these very long quasi one-dimensional segments. If you dope away further, you immediately recover some kind of typical 2D Fermi surface again, and our claim is that this quasi one-dimensional segment actually leads to this marginal Fermi liquid that was proposed by Chandra Varma in 1989. What we now do is we perform Boltzmann theory on this band structure. So we calculate the scattering rate of momentum by summing up all the scattering events from momentum K prime, which are addressed now by this susceptibility, which in this case, it's a transport susceptibility. And so the transport susceptibility also includes this velocity vertex, which is taken into account in our calculation. And doing now this, on the tight binding model, we obtain the following result. Indeed, if we dope slightly away from the Van Hove singularity, we obtain a linear behavior here. And immediately, doping more strongly away, we immediately get this typical Fermi liquid behavior. So this quadratic behavior in temperature. So this was very promising. And what we also see that there is a crossover. at a certain energy which amounts to 6 Kelvin. And this is due to the fact that you have the Van Hove singularity very close to the Dirac cone in energy. And if you excite now, thermally excite these particle-hole pairs, they are actually in the vicinity of the Dirac cone. And here you actually have Fermi-liquid behavior. So it's not surprising then from here on, you have this quadratic behavior. But what is measured in experiment is the resistivity. And this amounts to an additional summation of K. And due to the reduction of phase space, there is a cancellation of this factor T, and therefore in both regimes, we obtain a linear behavior when we are close to the Van Hove singularity. And of course, when we are away from it, it is a typical Fermi-liquid behavior. So this was very promising, and we thought that there should be a more fundamental mechanism behind it. So this leads to marginal Fermi-liquid theory. And we calculated the self-energy also perturbatively in the Hubbard U. The formulas look quite similar, and the real part is obtained then with Kramers chronic relation. And indeed, we obtain what is coined the marginal Fermi-liquid phenomenology. And this is that the imaginary part of the self-energy is proportional to omega. And the real part is then dressed, but this is not surprising, by this Kramers chronic relation, by this logarithmic correction. And this is both seen in the numerics. This logarithmic correction should have consequences at, for example, other transport properties or thermodynamic properties. Heat capacity should have it, thermal conductivity should have it. But to our knowledge, this is the first model, microscopic model, that can really give a marginal Fermi-liquid behavior with only invoking a short-range Hubbard U interaction. And this is promising, and might also, we are thinking about trying to extend this to the typical Hubbard model, where maybe by distorting the Van Hove singularity again to this extended Van Hove singularity, also in this model, there might be something present, such as this marginal Fermi-liquid behavior coming from this microscopic model. Let me very briefly also comment our work on interaction effects. So far, we were always starting with band theory that is non-interacting. But of course, during the workshop and experimentally and theoretically, there have been many works and talks hinting at the fact that it's crucial to include the interaction. Now, I was talking about general features. This was this Lifshitz transition that doubles the number of Van Hove singularities and this extended Van Hove singularity. And both of them, these features should hopefully also be present in an interacting theory, so including it via Hartree-Fock. We are not there yet. We are performing these calculations at arbitrary doping. So far, we have only done calculations on the tight binding model at half filling. So at half filling, we have some results, which I will briefly show you. We include the two basic order parameters of graphene, which is this chiral mass, where you have a different mass in A and B lattice, and we have a hold-in mass that comes from this flux around one of these two sublattices. And due to the fact that you have now two different bands, you can also have different symmetric and antisymmetric combinations. And so this is the chiral symmetry breaking. This would be the Haldane phase symmetry breaking, where the two fluxes are both clockwise or anti-clockwise. And here you have the order parameter where the flux is in different directions. And this actually amounts to a valley symmetry breaking, because then you have two different energy levels of the Dirac points, which then breaks this valley symmetry. So our results are the following. We did our calculations for the screened interaction, where we assume that there are metallic gates close to the twisted bilayer graphene, and then also for the non-screen for the long-range Coulomb interaction. And what you see is that there's a difference at the strong coupling regime. So for boron nitride substrate, you would have a coupling constant of about 2 in these units. And you see that there's a difference in the order parameter. Here it would be this valley symmetry broken state, and here it would be the chiral symmetry broken state. We also see that there's a different transport behavior. There should be a transport gap here for the screened interaction and no transport gap in the long range. But what is interesting is that in both cases, there's a strong symmetry broken phase that signals a Haldane mass, which is in the intermediate coupling regime. And so it might be interesting also to look at this possibility if there is stronger screening due to higher bands of the twisted bilayer graphene. This is, the final comment is, this is actually very close to the magic angle. This peak here disappears when we go away from the magic angle. All right, so this was the first part of my talk, and now I want to come to a different topic, and this is the chirality and the magnetic response associated to it. And in order to define what I mean by chirality, let me start with the definition. And my chirality in that sense is really related to the old Greek word of hand. And so I refer to it as a three-dimensional object whose mirror image does not match the original. So you cannot superimpose it. The point is that it's really a three-dimensional effect. And I mentioned this because we are talking about mostly 2D, but in this case, it's a three-dimensional object that we require. As you know, different enantiomers are absolutely equal in most of their categories, and the only possibility to distinguish the chirality is by interacting with another chiral object. And this other chiral object is usually circularly polarized light, and where you change the polarization by propagating along, and you can define this chirality or quantify it by this formula here. And so this chirality, which is a conserved quantity, you can also define a chiral flux, is proportional to this frequency omega and to the intensity. So it makes sense to call this a chiral, or to quantify it as a chirality. Now, if you want to make and to see this chiral interaction, you need to go beyond the dipole approximation. So even though this is small, usually, you have to include it because this is this dimension in the third direction, in the three-dimensionality, which gives all the effect. And this introduces a different scale, a new scale, this is the wavelength of light, and A is the extension of the chiral molecule. And this is usually very small. And therefore this circular dichroism, so this difference between absorption cross-section of plus and minus circularly polarized light, is also small. Now, it would be nice to have this large, or of order unity. And so how can we achieve this? I mean, there's a mismatch in scale, and you can either make the chiral molecule larger, or, and this is the other direction, you can try to make the light smaller. So you kind of squeeze light, and these are the plasmonic or polarionic states. And we want to pursue this, and I want to show you that this is possible in these atomically thin van der Waals heterostructures. So far, this is a small effect, but it has been measured. It has been measured in the group of Park at the Cornell University. And let me also mention this nice theory work by Eric, Leonor, and Louis Bray, where they can understand and link this to a microscopic quantity, to a microscopic model, and explain this optical response. Our question now was, is there also a signature at the DC limit, so at zero frequency? And if you look now at the conductivity tensor, which is the basic quantity here, you quickly see that there's not a lot of possibility if you stay in a 2D system. So you can either have optical activity if you break time reversal symmetry, then you have this Hall conductivity, or you break rotational symmetry, then you have this birefringent system where you have a different conductivity in one direction than in the other direction. So X and Y is different. But all other, if you have these two symmetries, your conductivity tensor will always be proportional to the unit matrix. And the only way to get this effect is to break the two-dimensionality. So this is the minimal model to see optical activity in the DC limit. And it looks the following. So this is the first layer. And then you have to treat the second layer separately. And now you see that symmetry allows for this term here, which is very close to this Hall conductivity, but you see that it's perfectly symmetric. So Onsager's relation are fulfilled and you have a symmetric, time symmetric matrix. Okay, so we have to calculate the following response functions for all the different directions and layers. And these are 16 different quantities, but they boil down to only 3 different conductivities. And this is the in-plane conductivity labeled by sigma 0. Then you have the covalent drag between the layers. This means that you have a current in one layer and this drags a current in the other layer, but in the same direction. This is called sigma 1. And then you can also have this Hall coupling, and this means that you have one current in X direction, and this one drags a current in the Y direction. And these are complicated functions in frequency, but you can kind of condense them in Drude weights, and so this is the Drude weight 0, 1, and this chiral Drude weight. Okay, so with this at hand, we can discuss it. And it was not clear from the beginning if these are actually non-zero, but it turns out that they are non-zero. So this is the chiral Drude weight here I'm presenting. And it's 0 at the neutrality point, but then it is always positive for the whole regime, and it's negative for the electron regime. And so this is very similar to the Hall effect, where you also have this ambipolar response. And we dub this the longitudinal Hall effect because an in-plane magnetic field gives rise now to a current that is in the direction of this magnetic field. And the proportionality is given by this Hall Drude weight and also by the distance between the layers. So it's a small effect, but hopefully measurable. And you see that there's a conservation of chirality because when you flip now the twist angle from plus to minus, you just flip down the curves here. So this was interesting, but here I started the video already, so let me do it again. But close to the magic angle, you actually have a change in chirality. So this chirality does not always obey the chirality of the underlying atomic structure. So let me show you this. So this is the chirality. Here you have a twist angle, and I'm decreasing the twist angle, and this is the doping level of your system. And you see that at some certain critical magic angle, you have a perfectly flat and change of chirality. So this is this crossover. And we wanted to discuss this in more detail, but it's very difficult if you do this from this formula, because there you have to do Kramer's chronic and it's numerically very unstable. So we were happy to be able to come up with a formula for this chiral Drude weight. And this formula is very similar to what is seen normally in the density of states, but this time it is stressed. So you have this, this kernel here, and this kernel is the vector product of a sheet current in one layer with the sheet current in the second layer. So this is the definition of this chirality, which comes also from a different response theory approach. And now we can calculate this easily, and we see that in the DOS, as you know, there's this, these van Hove singularities that merge in this magic angle regime, which is strongly enhanced here. And for the chiral Drude weight, we have a different regime or a different behavior. The black line always signals that there's a sign change from positive to negative. So for large angles, there's this sign change due to approximate electron-hole symmetry. But then at this magic angle, you see that there's a long and constant sign change between one regime and the other. And interestingly, there's another one here where you also have a sign change. Here you also have a sign change. It's very hardly seen in the color scale, and here again. So we were trying to understand it. We have not completely understood it. And I just tell you now what we so far understand, and I think there are several open questions. Well, first of all, there's an emergent C6 symmetry, and you can kind of quantify it by looking at this difference between the electronic bands of kx and the electronic bands of minus kx. So there's a zero at one critical angle, which is the magic angle. Now, you also have an almost zero at 50 and the 60, and this one corresponds to this and this crossover. So this makes sense. Let me also tell you that the change or the cancellation of chirality is highly non-trivial. So for different, this is the kernel, so the cross product between the two currents, and it's by far not zero. But when you sum over the different Fermi lines, they sum up to zero. And another observation we make is that why do you have such a wide energy window where it becomes zero? So this has nothing to do with the flat band anymore, but it's a cancellation of the chirality of the first remote band and the second remote band. And if you're away from the magic angle, you see that there are plateaus which are almost quantized with respect to commensurate angles. So we don't understand really in detail this cancellation and why it extends to such wide energy range and goes to the remote bands, but this is work in progress. Let me continue with this plasmonic response and remind you that plasmons are charged. Okay, I think there's a question. Now I saw it. If it is not phonomediated, is there any experiment showing what happened? Okay, I think this is a different question to a different topic. I will postpone this question. Sorry. Okay, so let me continue with this with the plasmons, and so electric dipole oscillations that are confined are called plasmons, and due to the response now, you will always have a current oscillation that is transverse to it. And this one is in two different directions. And this means that there's a loop, and if you have a current loop, this of course is associated with a magnetic moment, which is in the same direction as the electric dipole moment. So you have this electric dipole moment, which is collinear with the magnetic dipole moment. And the proportionality is this factor chi and the distance between the two layers. And we calculated this, this quantity, which is related to the chiral Drude weight and the total Drude weight. And you see that there's considerable strength. It can go up to 30 in this dimensional quantity. And this opens up now the following. We can quantify this also in the chiral near field. So let's see if the chirality of the electronic system is also passed on to the chirality of the electrodynamic system. And this is the case. So we calculated this quantity, this chirality, and compare this chirality with the one of circularly polarized light. And this is strongly enhanced due to this field confinement, and seems to be one of the strongest chiral light sources without breaking time reversal symmetry. And we kind of envision now the following setup. So for example, you have the synthesis of amino acids close to twisted van der Waal heterostructures, and you excite plasmons, then you might only synthesize one enantiomer, so only L or only D amino acids, or you could create other different molecules, so catalyze reactions which are actually not possible in real ambient conditions. So this is kind of a proposal, and might be worth thinking about it, and to play with this possibility of having this additional degree of freedom at hand. So this is the last topic of this chiral response, and this is now not related to this chiral response exactly, but it's related to this D0 and D1 Drude weight. And what I mean by this is that the susceptibility to an in-plane magnetic field is given by this quantity. And usually this quantity is positive, and therefore you have a diamagnetic response. But close to half filling, this changes sign, and actually it becomes paramagnetic. This means that there's a negative Drude weight in the in-plane. So it would mean that the electrons are really going opposite to the field direction. And this effect is maximum at the magic angle. And this observation led us to see what happens in transport experiment. So we considered a nanoribbon located and attached to leads, and then we put another additional layer of graphene on top of it. So the leads were only attached to the lower layer, and this means that there is a effective magnetic field actually acting. At large twist angles, actually you don't see any strong connection of the two layers. So you see that the density of states is quite different between the two. But when you're at the magic angle, you see that the current especially is strongly localized, and they are identical in the lower and in the upper layer. And they are strongly enhanced also. So you have a strong current enhancement that is 10 times larger than the incoming bond current. And you have these whirlpools, and these are at these AA stacked regions. So this is a strong effect, and we were looking at the current distribution here. And when you look at the counterflow, so we are only looking at a current flowing in this direction and a current flowing in the other layer in the other direction. And this means that there's a loop current. And you see that there's a highly directed current flow from one source to one drain. And this means that there's a loop. And if you have a loop current, this means that there's a magnetic moment attached to it. So each of these high counterflow current profiles have actually a magnetic moment attached to it. And the total current is an order of magnitude smaller. And the total current, moreover, has this vortex structure. So in total, this cancels out the total current in these patches, and therefore we can define a magnetic moment, which is normally not possible, because remember, we are in a non-equilibrium situation. And so we have now the situation that you might think about electrical control of magnetic excitations. And if you put it on your wish list, since you can have an interaction between these magnetic moments, and you can tune them by the twist angle, the distance between them, and thus the interaction, maybe there's even something like spin liquid behavior. All right, so this is more or less what I wanted to talk about. Let me briefly comment also on other works on twisted bilayer graphene, just to make some advertisement. We recently published a work on flat band magnetism. This is relying on this theorem of Andreas Mieke that shows that for a flat band, there's a unique ferromagnetic ground state up to spin rotation, of course, if the density matrix is strongly connected, so it's not separable. And we did calculate this density matrix for the flat bands of graphene. So this is the diagonal elements of the density matrix. This would be a off-diagonal element. And no matter how to change the parameters, so we did many different parameters. We put relaxation and knot and displacement field up and button down, and we always observe that there is that the density matrix is strongly connected, and this hints to the fact that there should be a ferromagnetic ground state, a stable one at n equals 0, and also if you create a gap at the direct point, also at filling factors plus and minus 1, plus and minus 2, so half filled in the conduction and valence band. Let me also show you and tell you that we calculated these interband plasmons already some time ago in 2016. This was now observed nicely by Van Koppen's group. They observed this resonance here, which is here in this graph fitted to a Fano resonance. So this shows that this is really a localized state that is hybridizing with this continuum of electromagnetic modes. And it is important actually for the appearance that there's a change in response, in the static response. So there's a crossover from linear response to a quadratic response. And this actually enables then the appearance of these true plasmonic modes. Let me also highlight this mode here, which is very flat and low in energy. This one can be highly tuned with the twist angle. So the resonance follows a linear behavior, and we can now fit this with a Lorentzian and now make a crude model that this mode is actually resembled by a delta function at some energy where this mode appears. This constant here, C, can be obtained from this fit to a Lorentzian fit. And then using Boltzmann theory, we obtain that there's actually a linear behavior in the scattering rate. So this is, again, another mechanism to get this, marginal Fermi liquid phenomenology. So maybe this might be another candidate for superconductivity. And last, let me highlight a work that was recently posted on the archive, where the main player is Louis Bray, who initiated this work. It is related to small angle twisted bilayer graphene, where in the presence of a displacement field, you create a gap, and due to the lattice relaxation, there's a close hard interface between the AB and the BA lattice, and this gives rise to topologically protected states. And this network of states can be now, or will, we have modeled this with an alternating Hall conductivity. And this microscopic model gives now rise to plasmonic resonances and to a plasmonic dispersion, which is characterized by these Dirac points. And this is, of course, now speculation, but you can, if you concentrate now to the low energy regime, you can open up these Dirac cones. You can do this with the same mass or with different mass, and then in the case where you create a holding gap, you would kind of envision some topologically protected plasmonic currents that are carried by topologically protected electronic states. So it's a nice an exotic state that might show up in these systems. So with this, I'm completed, and I would like to acknowledge my collaborations from my institution, the CSIC, the National Research Agency of Spain. I would like to acknowledge, first of all, Jose Gonzalez, who did the work with me on the superconductivity, Heinrich Kohler, and Luis Bray, Tatiana Slipchenko, and Luis Marti Moreno on the plasmons. Also, many thanks to Guillermo, who is at the Autónoma of Madrid, Tony Lowe at Minnesota, where we worked on chiral plasmons, Dario Boamon, he's in Sao Paulo and worked on the transport, and Rebecca Pons, she was a master student with Andreas Mielke on this ferromagnetic instability. So thank you very much, and now I'm open for more questions. Thank you.
Okay, thank you very much. Let me give you an applause on behalf of all the attendees, but they are silent, so they cannot clap. But they can ask questions, and they are doing so. So you can see them in the Q&A. I think you skipped one. You are with the question of Juan Carlos, I believe. The other ones have been answered. So. Okay, so
the question of Juan Carlos is, if it is not phonomediated, is there any experiment showing what happens with TC when the bilayer graphene is formed with carbon-13 instead of natural carbon-12? Yes, I mean, this is good questions. I think I pass it on to Frank. So I don't know if there are some ideas of including carbon-13 instead of natural carbon-12 in this twisted samples. This would definitely would be able to probably resolve if it's phonon-mediated or electron-mediated.
I'm not aware of these activities, at least not if anybody is carrying those out, but clearly this would be very relevant to do. I think the combination of obtaining high quality crystal and then making twisted layers out of carbon-12 and carbon-13 is a significant challenge, especially because TC is not the same from sample to sample. So
yeah, that's another crucial point. Yeah, you cannot really prepare even with carbon-12 exactly the same sample again. Yeah. So this will change TC. But I mean, it would be interesting to see if there's a significant reduction of TC. Yeah.
Yeah, if it would disappear or something like that. Yeah. Okay.
There's another question. Are there any experimental results that you know regarding the synthesis or stereoselectivity of enantiomers using twisted van der Waals heterostructure? No, I actually, I would like to see some experiments if this is really possible to enhance. So the quenching mechanism should be strongly depend on whether you have a left or right twisted van der Waals structure. And of course, you need to have some chiral molecules which are active in this frequency range, but maybe Frank is also the expert in that, that might be able to resolve it.
Yeah, it's a great idea. Somebody should do it. Nobody will do it, we will do it. So is that it? So please feel free to type more questions or raise your hand if you want to answer ask your question. There is a hand raised, so I will let you speak. 2 hands also. Wait 1 second. Somehow I'm not able to make somebody speak. Mercedes, if you are on the line, can you allow me to allow people to speak?
Yes, right away.
Okay. Mercedes is solving everything. She's responsible also for the technical implementation, and she's doing a great job. You see, now I can allow Juan Carlos Idobo to speak. So please ask your question.
Thank you very much for the really nice talk. My question is regarding the second part of your talk regarding chirality. You talk about circular polarized light. I'm wondering what will happen if instead you use vortex beams, which have like, this twisted light that carry orbital angular momentum, and instead of using just plus minus h bar, these vortex beams will carry higher orbital angular momentum such that the selection rules will be different. Have you thought about calculations on that area? Thank you.
Yes, actually, you mean this topological light, probably, where you can have really huge momentas up to 100 or so, if I'm correct, or even larger. This is another way, but all of these light beams are, of course, propagating light. So we are now trying to confine this sort in twisted bilayer graphene, and would be interesting to have more understanding of how this light field can then be modified, maybe also in the direction as you're pointing out, with different light beams that might then create also different confined light. So the idea here is that this chirality that is also present in the electronic response is actually then passed on to the chiral field, the chiral near field. And how to modify this and define this in more elaborated ways, I don't know, and it would be interesting to see, yes.
Thank you.
Okay, so this one, yeah, another question comes in now from Chunli Huang. Paco mentioned the shape of the bands are heavily renormalized by the Hartree potential. And how does this affect your proposed mechanism of superconductivity?
No, this is an excellent question, and we are working on this at the moment. One of the problem is why we have not yet results is the fact that we are trying to do this with the tight binding model, and now doping your system with the tight binding model and doing it self-consistently, and checking out all the parameter space is very costly. And so far we have seen also a strong renormalization, but only centered at the Dirac point. And now we continue these calculations at half filling and or pinning the Fermi level always to the Van Hove singularities. And so far I cannot give you any definite answer, but our hope is the following, that these universal features such as this doubling of the Van Hove singularity, so that there is a Lifshitz transition at the Van Hove singularity, and also this extended Van Hove singularity, that they will survive actually with renormalization. So this is not so much linked to the band structure, but this is yet to see. So I cannot answer your question, unfortunately.
Okay, great. I see at this point no more questions. Well, I have many, but I'll discuss them with you privately. So last chance, raise your hand. We're also at this time for the break, but if you are quick, you can still raise your hand now and ask Tobias. If not, feel free to contact him anytime. Okay, great. Thank you so much.
Thank you very much, Frank, for this opportunity. And all of you for listening. Thanks.
Okay, thank you everybody for joining. See you then at the next session, I believe at 4:30. Yes. Okay, thank you. Bye-bye.
Okay, thank you, Fran. Thank you, Tobias. I will see you next session. And yes, it's 4:30, and we'll be back in a while. Bye-bye.
Perfect, thank you.